This is to welcome you to our union session on the consequences of this unusual sunspot minimum. We're going to be hearing papers on various aspects of the minimum, including luminosity and history and energetic particles right to the present. So let me call the first paper, which is Solar Magnetic Field and Irradiance, How Unusual is the Current Minimum, given by Solanki. As I said, we'll let you know after when you have 3 minutes to go. It's 15 minutes.
Okay. Where do I, this is the right or this one? Okay. Okay. So, good afternoon, ladies and gentlemen. Let me begin by asking the question, why should we give a damn? Why should we study the current minimum? What do we hope to learn? Now, there are a number of things that we hope to learn from that. And the first is, if we want to understand and if we want to find out if the sun influences the Earth's climate in any significant way, then we need to know what the solar irradiance has been doing in the past, and not just its cyclic variation, but also if there is a secular trend and by how much it has changed between, for example, the Maunder minimum and now. If you want to understand what is causing any long-term change of the irradiance, we need to know what the magnetic field has been doing, if that shows any secular trends. The structure of the field and its evolution, its interaction with motions in the sun's interior or surface, for example, with convection, drives not just the irradiance, but many other things also: solar activity, the structure, temperature of the corona, and even properties of the heliosphere. As a little side effect, or as a big side effect, the present minimum will provide us, or hopefully will provide us, information, new ways of testing dynamo theory and trying to understand how the magnetic field is generated and what causes its evolution. And as a final side effect, we have learned something also about the sociology of solar physics, of how mature our science is. One of the definitions of a maturity of a science is that one can make predictions. And to my knowledge, at least, there was no serious prediction about what this minimum was like, which puts us in about the same ballpark as economists. Now, that's a pretty worrisome thought, I think. So let's move ahead to the question, how unusual is the present minimum? And I'm just going to talk about global properties here. Right? There are many details which are different, but let's just look at the big picture, so to say. What you see on this diagram is, in the last 45 years, the heliospheric magnetic flux, which is the thick blue line. And if you follow it, you'll find that in the last couple of years, it's been lower than at any time in the last 45 years, which is basically the whole space age. That's the period of time where we could measure it. And so definitely unusual, but that's not a very long period of time. If you want to go much further back, then you need another proxy, and sunspots are a good one. We have 400 years of that. And if you look at the number of sunspots, that's the shading, the light blue shading in this diagram, also for the same period of time, the last 4 cycles. In the present minimum, we have had 762 spotless days as of December 1st. And this is way more than any of the previous 8 minima before that. It's more than twice the average number that we have had in these previous 8 minima. So yes, indeed, the current minimum is unusual. However, if you go further back in time, the 4 minima before that, let's say the second half of the 19th century, this was not unusual at all. We have had, in those 4 minima, you've had similar numbers or even more spotless days during a given minimum. So It's an unusual minimum, yes, but it's not an unusually unusual minimum. If we go closer to the sun, then we expect the heliospheric field to be driven basically by the magnetic field at the poles of the sun. And this is a diagram that you have seen if you were in the session on Monday afternoon, like the previous one as well. What's shown here is as a function of time from 1976 till now, the polar magnetic field of the sun as measured by Wilcox Solar Observatory, and the minima are given by these extrema, right? The horizontal line in the middle is 0, and you see that at the current minimum, the polar field is only about half as strong as it was in the 3 previous minima. So, again, unusual, but again, not a very long period of time that we are comparing with. And this is consistent. Having it about half as strong in the polar field is very much consistent with having a heliospheric field, which is also roughly half as strong as it was in the previous few minima. Let's move on to the solar irradiance. The total solar irradiance, that means the brightness of the sun as a whole, integrated over all wavelengths. Now, that's a much more tricky thing to measure. And it's also difficult for a longer period of time because you don't have measurements from the same instrument, and you have to put them together. And depending who does that, they get somewhat different results. So what I'm showing you here is a composite put together by Klaus Fröhlich, the Davos composite. And you can see that in the period of time, since measurements started in 1978, there have been 3 cycles roughly. You see the 3 maxima, you see the 3 minima. The first 2 minima were at about the same level. The present minimum is lower by about 0.28 watts per square meter compared to the others. Just for comparison, the amplitude of the solar cycle in the total solar irradiance is about 1 watt per square centimeter. So, again, a new development there compared to what we had in the previous couple of cycles. Finally, let's consider the total magnetic flux of the sun integrated over the whole solar disk, or just looking at the center of the solar disk. And we find that in the present minimum, the amount of solar flux, magnetic flux, is only about 60% what it was in the minimum of 1996-97, even if you exclude the poles. So it's not just this open flux at the poles which has changed, but it's actually the very structure of the magnetic field. In the quiet sun, the amount of field you have in the network is considerably lower now than it was before. Now, this fits in quite well also with the fact that the irradiance is lower, because using this lower average magnetic flux that we have on the sun also implies that there will be a reduced total solar irradiance, so they fit together very well, and that again confirms previous results that the total solar irradiance variations are indeed caused by the magnetic field at the solar surface, which contradicts a recent paper by Klaus Fröhlich. But he didn't actually compare the magnetic field with the irradiance. He compared the magnesium index with the irradiance and found that they diverge recently. But if you look at the magnetic field itself, you find that it goes very well with the irradiance. Now, the important thing, the thing I find most exciting from all of this, is that for the first time, we are seeing a secular change in very basic parameters of the sun, in the total magnetic flux, in the open magnetic flux, in the irradiance. This is something we have been discussing for a decade or 2 even, but now we actually have direct measurements showing us that. That, I think, is the most exciting thing to have come out of this minimum. Now, can we explain such secular change? Yes, indeed, there is a mechanism. And it's based on having overlapping solar cycles. Okay? So if you look at the upper diagram for a moment, you see the individual dashed green curves as a function of time would be the amount of magnetic flux which is emerging at the solar surface. And if two solar cycles overlap in the sense that flux is still emerging in the old cycle while it has started emerging in the new one, the magnetic flux will never drop to zero between them. So you'll get a minimum where you have a certain amount of flux, and depending on whether the next cycle is strong or weak, whether it peaks early or late, the level at which you will have magnetic flux in the minima will be higher or lower. And you can get secular variations of this type. There are different variants of this, but that's the basic idea, okay? Overlapping cycles. You can then use this, make a simple model, put this in a few differential equations, and starting from sunspot number, we had shown already a number of years ago that you can produce secular variations in the total, in the open flux, and in the irradiance as well. Now, very recently, in a paper together with Luis Vieira, we have improved on the model. We have extended it by distinguishing between rapidly and slowly decaying flux. It doesn't change anything in the very basics, but what it does is it improves the correspondence with the observations. And just an example, you see in the lower diagram the total magnetic flux, the total time series that is available to us starting in the 1960s with Mount Wilson and then Wilcox and Kitt Peak coming in as well. So these are the colored symbols. Those are the measurements. The black line is what the model gives. And in particular, if you look at the last few years, the model agrees very well with the data, even in this time when the flux has fallen to lower values than we had before. And the nice thing is that we did not use this period of time to constrain the model's free parameters, right? We stopped there where that vertical blue line is at around 2001. So the rest is just what comes out of the model, and it agrees quite well with the data. You can do the same thing for the open flux, which is given in the upper diagram, where we are comparing the model, which is the blue curve, I think, with the reconstructions of the open flux by Mike Lockwood and co-workers, which is the black curve. In the lower diagram is the comparison with the irradiance. In both cases, where the open flux has fallen low and the irradiance has gone down, the model is going along with the data. Again, we didn't use this most recent period to constrain the model. Now, if you listen carefully 2 slides ago, you will be wondering now, what did they do about cycle 24? Because remember, we are talking of overlapping cycles. What we did about cycle 24, because we don't know how strong it will be, we just assumed there is no cycle 24. So there is no cycle 24 in this model, and the model then reproduces the data extremely well. Does that mean we are going to go into a Maunder minimum-like event? I don't think so. This is not the most precise way to make predictions for the next cycle. Okay? But what it is suggesting to us, I'm not saying it's telling us, what's suggesting to us is that cycle 24 will either be weak, or it will peak late, or some combination of these. Okay? Now, if we assume that the model is not doing too badly, since it does reproduce the data quite well, we can then compare where we are compared to the period of the Maunder minimum. We can go back all the way where we have sunspot data, 400 years, or 300 years in this case. I've just plotted since the end of the Maunder minimum. And you see, yes, the flux has fallen quite a way, but it is nowhere near there where, at least according to the model, it would be in a Maunder minimum-like state. We haven't even reached, if you look at the lower diagram, it shows the open flux. We haven't even reached the levels where, according to the model, we would have been in the Dalton minimum, around 1800, when there were a few very weak cycles, and the open flux and also the total flux were very low. So basically, we are at the level of around the 19th century, which is interesting because also the minimum as far as the sunspots are concerned is also like the minima that we had during the 19th century. Okay, we come to the conclusions. The current minimum has demonstrated that both the magnetic field, the total flux, the open flux, whatever, and the irradiance display secular variations. I think this is an extremely important result. This is something that we have been discussing for years, for decades. There were indirect indications for that. Now, finally, we have direct proof, direct measurements that this is the case. What I'm quite happy and relieved about is that even the simple models that we have constructed for the evolution of the magnetic flux reproduce the data relatively well, including this unusual present minimum that we have, although this was nothing that we tweaked the model to do. It came out naturally. And finally, the behavior of the present minimum suggests that the sun is returning to an activity level compared to what we had in the 19th century. Or, even beyond that, not just the 19th century, but actually during most of the Holocene. The diagram you see here is the number of sunspots, or the sunspot number, reconstructed from carbon-14 data over the last 7,000 years. We have put in two different bars. The blue one at the bottom, whenever the sunspot number fell below that value, we said the sun is now in a grand minimum state. You see there were a number of these grand minima, but there have also been times when the sunspot number was very high over those red values, when there were grand maxima. And the last 50, 60 years has definitely been a grand maximum, and one of the strongest ones we have had. And it looks like the sun is now leaving that grand maximum. Where it's going to, I don't know. I think we have really exciting times ahead of us. Thank you very much.
Which is solar magnetic field and irradiance. How unusual is the current minimum? Given by Solanki. As I said, we'll let you know after when you have 3 minutes to go. 15 minutes.
Okay. Where do I, this is the right or this one? Okay. That we hope to learn from that. And the first is, if we want to understand, and if we want to find out if the sun influences the Earth's climate in any significant way, then we need to know what the solar irradiance has been doing in the past, and not just
this is to invite, welcome.
So, good afternoon, ladies and gentlemen. Let me begin by asking the question, why should we give a damn? Why should we study the current minimum? What do we hope to learn? Now, there are a number of things.
Welcome you to our union session on the consequences of this unusual sunspot minimum. We're going to be hearing papers on various aspects of the minimum, including luminosity and history and energetic particles right to the present. So let me call the first paper